Okay, so we're going to try out. We're trying to teach you a new lesson on appliances and efficiency. I'm using a new recording device today, so something might not work properly. But we're able to work out the efficiency of an electrical appliance. But to start off, what are the names of the three wires in a plug? How can you put these devices in order? Of the highest power usage to the lowest power usage. A lamp, a kettle, a vacuum cleaner, and a phone charger. What type of useful energy do the following appliances give out? A lamp, a kettle, a fan, and a toaster. And which wire in a plug is connected to the fuse? Sorry, I have to just tell my dog off. It's fine. What are the names of the three wires in a plug? Put the devices in order of highest power usage to the lowest. What type of useful energy do the following appliances give out? And which wire in a plug is connected to the fuse? Pause, and once you've done, unpause and let's check your answers. Okay, three wires in a plug. We have the earth, we have the live, and we have the neutral. Can you put these devices in order of the highest power usage to the lowest? Well, the highest power usage, I've told you many times, is a kettle. In fact, I'm going to show you that later. It uses about 3,000 watts. Then after that, we've got a vacuum cleaner. Then we have a lamp. And then a charger. Because the kettle produces a lot of heat very quickly. A vacuum cleaner doesn't make heat, but it does have movement. So the fans and the spinners. A lamp produces light. A phone charger doesn't really produce anything. It gives energy back to the battery, helping it recharge and do more work. It doesn't actually give anything to the battery. What type of useful energy do the following appliances give out? Well, a lamp gives out light energy. Light. A kettle and a toaster both give out thermal. And a fan gives out kinetic. Which of the wires in a plug is connected to the fuse? That is the live one. And that's connected to the fuse. Okay, so we'll see later, and I think you saw in the other one, that when we're talking about energies related to a particular device, things can use thousands, if not millions of joules of energy. And actually, when we're talking about millions of joules, it's a really big number. And if we worked out actually how many joules of energy your house uses in a month, it'll be millions, maybe billions. It reduces an enormous amount of energy. And so when you get an electricity bill when you're older, or when you pay for electricity, they don't charge you in joules because the number of joules would be so much. What they do is they convert it to something else called a kilowatt hour, or a unit. And basically a kilowatt hour is the same as how much energy you would use if you had a kilowatt device running for 1 hour. So something that runs on a kilowatt is probably I don't know, maybe a toaster. A kilowatt. So if you had a toaster running for 1 hour, that would be the equivalent of 1 kilowatt hour. A kilowatt, if you remember, is 1,000 watts, and an hour is, if we put it in seconds, is 60 times 60 seconds. That's not do 60. 3,600. So 1,000 times 3,600. A kilowatt hours is actually 3,600,000 joules. But for simplicity, they just call it a unit. So if you see an electricity bill, you might have used 18 units in the last few months. That's 18 times 3.6 million. So take a moment, pause, write that definition down. 1 unit is 1 kilowatt hour, and 1 kilowatt hour is 1 kilowatt for 1 hour. Write it down. Okay, so let's have a go. Work out how many joules are created for these different things. Let's do this as an example. A 5-watt torch, 5 for 50 minutes. So that is 5 times 3,000 seconds is equal to 1, 5, 1, 2, 3. 100 watt lamp in 24 hours. Okay, so that's 100 times 3,600 times 24, which I'll have to do on my calculator. Is 8,640,000. Yes. Calculate how much energy is transferred when a 3 kilowatt kettle, 3,000 watts, is used for 5 minutes. 6 times for 5 minutes each time. So 3,000 watts times 5 minutes, which is 5 times 60 times 6. 3,000 watts, or 3,000 kilowatts, 5 minutes, so 5 times 60 seconds in a minute, times 6 times, gives us 3,000 times 5 times 60 times 5 is 4 million. 4.5 million joules. So you can see, if we talked about using a kettle 6 times, okay, it's 4.5 million joules. So that's just a kettle. I've used a kettle more than 6 times in my house today. So if I were to get my electricity bill and it tells me about joules, it'd be talking about millions and billions of joules. But that's if I talk about a lamp on for a day, that's 8 million joules. So talking about energy, electrical energy in joules, is a huge number. So they normally talk about it in kilowatt hours. I'll leave the last one for you to do. 1,000 watt microwave used for 30 minutes. 1,000 watt microwave used for 30 minutes. Convert 30 minutes into seconds. Done. Okay, so I need you to spend a few minutes copying down this table. So pause, copy down the table. You need to take out the full width of the book. You're going to have to do some calculations. Pause, copy down the table. I hope you've done this, otherwise everything else is going to be very difficult. So we're just going to do it in steps. So the first thing I want you to do is work out energy per day in joules. So the energy per day in joules, remember, energy is equal to power times time. So the power is in watts. 2,200 times the time, 3 minutes times 5. So we're going to do 60 seconds times 3 times 5. And all of that will give you the energy. So I'll do this one for you. Which is quite a lot. 1,000,000 9 8 0 0 0. Oh no, not 1,000,000. 198. No, that is 1,000,000. 1.98 million. Energy per day in kilowatt hours. I told you before that 1 kilowatt hour was 3,600,000. So if we do whatever that previous answer was, 1.9 divided by 3.6 million gives us, so 198 1 2 3 4 divided by 3600 1 2 3 equals, for this one, 0.55. So 0.55 kilowatt hours. Okay, if we do it for the whole year, 0.55 times 365 65 times 0.55 gives you 200 kilowatt hours. And a kilowatt hour is roughly 11p per kilowatt hour. So let's do 200 times, if it's in pounds, we'll do 0.11. So it costs you £22 to run your kettle for a year. Not for the whole year, not as in like for the whole year, but if you use it all those times, it costs you about £22. Can you do the same for the next two? One is a very, very high power usage device, an electric shower. The other one, an incredibly low usage device, your broadband router. So do exactly what I've done for the electric shower and the broadband router and work out how much it costs for each of them. Pause, fill in those, and then unpause when you're done. Okay, now the power rating on the devices tells you how much electricity they use, how much electrical energy they used. How much electrical energy they've taken from the mains, but they don't always use all of that for the greater good. For example, in this diagram we have a very classical diagram showing the energy usage in an old school light bulb. If a light bulb takes 100 joules of energy, it used to just give out 10 joules of energy as light and then 90 joules of energy as heat. That's why those light bulbs aren't used anymore. Now we have LED bulbs. LEDs are better. But in the olden days, and I'm not talking that old, like 10 years ago, light bulbs used to use so much energy for heat. They wasted so much energy as heat. They were really inefficient. So for that light bulb, useful energy out, you only got 10. Where's my pen gone? So that would be 10 divided by, well, I got 10 energy out as joules, 10 joules out as light, but I put in 100. So that gives me 0.1. If you times that by 100, means 10% efficient. 10% efficient isn't very efficient at all. So many devices may waste a lot of energy. Let's have a look. I did a little experiment. We'll discard this for a second. Right. Okay, so I'm going to try a little experiment right now. I've got a kettle. Kettle's empty. Don't judge me. It needs to clean inside. And I've got this is a thermometer. It's a cooking thermometer. It's got a little bit of metal at the end, and you stick in your food to see whether your food is cooked. I've got a jug that has 500 milliliters of water, which I'm going to put into my kettle. So I know exactly how much I've got in. Like that. I've also got this strange little device, which is basically it's a power meter, and it tells you. I'm going to reset it. It tells you how much electricity you're using for different devices. So my kettle is plugged in to this thing here, and what I'm going to do is I forgot to take the starting temperature of the water. I'd already just boiled the kettle before, so actually it'll probably be above 20 degrees. Yeah, well, they're not very fast, this thermometer. 22, 23. £23. Okay, that's cool. Put the lid on the kettle on. We can change this, so this is currently reading kilowatt hours. That's how many volts you've got through it. Frequency of 50 hertz because it's plugged into the mains. I can tell you the current, but I think we want the watts. So I need a timer. Give me a second. Okay, so the only timer I could find is my daughter's Kindle Fire thing. So what we're going to do is we're going to turn the kettle on, start the timer, and see the kettle is boiling. It's quite difficult to hear. Obviously the kettle's boiling, so I'll step away whilst I talk. But basically this is working at 3,000 watts. It takes 3,000 watts, so that's 3,000 joules every second. It's jumping a bit. 2006. But that's roughly 2006. It's taken 30 something minutes, 30 something seconds. How long is it going to take? 40 something seconds. 50 seconds. Oh, as it boils, the power starting to go down a bit. But roughly 3,000 the whole way. Hear it. Stop that there. It's a bit hot, obviously, because it's just boiled. Let's just prove that it has boiled. Let's stick the thermometer in, see how long it takes. Oh. So it's about 100 degrees, and it took 1 minute and 10 seconds, so 70 seconds, and it was running at 3,000 watts. Is it still drawing out 3,000 watts there? Hopefully that's probably the last thing it drew out. Okay, we can work out how much, what was the total amount of energy it used, and then how much was used in heating up the water. Okay, so I put in 500 millilitres of water. Now 500 millilitres, handily is 500 grams. 1 milliliter is 1 gram, so 500 millilitres is 500 grams, or half a kilogram. We saw that I measured the temperature and it was 23 degrees at the start. At the end it was 100 degrees because it boiled. So we had a temperature change of 100 minus 23 gives us a nice 77 degrees. Now, in the next unit, I'll be teaching you with something we're learning about specific heat capacity. And it lets you know, work out how much energy is required to increase the temperature of water. So the specific heat capacity of water is 4,200. Now, if we multiply this specific heat capacity by how much water we had in kilograms and its temperature change, we get the value of 161,700 joules. To make 500 grams of water increase its temperature by 77 degrees, we have to give it 161,700 joules in total. That's what you need to give it. The kettle was running, if you looked at the video, you saw it was running about 3,000 watts. Sometimes it was slightly higher than 3,000, 3009, 2016, and it ran for pretty much 70 seconds. So 3,000 watts is 3,000 joules per second, times by how many seconds tells us how many joules, and that gives us a total of 210,000 joules. So the kettle gave 2010 joules to the water, but the water only needed 161,700 joules for its temperature increase. So there was a loss of energy. In fact, could work out 161,700 will tell us how much energy was lost. Where was it lost? Well, you can see from the video that actually the kettle was really loud, so some of it was sound energy, and also it's not just the water that gets hot, the kettle got hot. So if the kettle's getting hot, then some of the energy that kettle's giving out is going to warm the kettle and the surrounding area. If we put that those numbers into the efficiency equation, the useful energy out, so the useful energy was 161,700 divided by the energy we put in, which was the kettle put in 210,000 joules. So that divided by that gives you 0.77, which if you times by 100 turns into a percentage. So my kettle is 77% efficient. It took 77% of the energy and did something useful with it, which was heating up the water. The rest, it wasted. In fact, here are some examples of efficiency. Use table 1 to answer the following questions, but it's good to look at them. So a filament lamp bulb I mentioned earlier maybe has an efficiency of 10-20%. A halogen bulb has an efficiency of about 25%. Whereas a fluorescent lamp bulb, which is one of those lamp bulbs that have those kind of strange shapes, they're kind of twisty glass, they're about 80% efficient. And an LED, they're about 90% efficient. It's asking you how much energy is wasted in 1 second by the filament lamp bulb. Okay, if it's 20% efficient, yeah, only, so 100 times 0.2 is, whoa, 20 joules per second is useful. Okay, so how much is wasted? 80 joules is wasted. Can you do the same for the CFL bulb? A student looks at table 1 and claims 50 LEDs would need to be given out the same output as the halogen bulb. Explain this claim is incorrect and estimate how many LEDs would be needed. Okay, so this one's at 2 watts and it's 90% efficient. So 2 times 0.9 means for every light bulb you get 1.8 watts out. For the halogen, it's 25% efficient. So you get, so every bulb you only get 25 watts out. Okay, so 1.8 times 50 means here 1.8 times 50 would be 90 watts, which is obviously more powerful than that bulb. So if we do what do we do? 25. We do 25 divided by, or 1.8. It gives us, actually we'd need about 14 halogen bulbs to have the same light output as 14 LEDs to have the same light output as a halogen bulb. So they weren't really questions, I did those for you. But now here's a chance for you to do some questions yourself. An electric heater is left on for 4 hours. During this time it uses 36 megajoules of energy. Calculate the power of the heater. Calculate how long it would take a 2000 watt electric kettle to use 36 megajoules of energy. The main power supply of a computer provides a current of 1.5 amps at 230 volts. Calculate the power supplied to the computer. In 1 month, the computer is used for 130 hours. Calculate how many joules of energy there are supplied to the computer in this time. Here's an activity for you just to help you become more familiar with efficiency as a percentage and efficiency as a decimal. So if a low energy light bulb, LED, is 0.90% efficient, that's 90%. So if 0.9, when you convert it to a percentage, is 90, 0.9 times 100 gives you 90. So the same for a filament bulb. If it's 0.2, times it by 100, that gives it as a percentage. Can you work out what it is for the halogen bulb and the electric heater as a decimal? You don't have to draw the whole table out, just write halogen bulb as a decimal, write down the answer. Lamp as a percentage, write down the answer, and a heater as a decimal, write down the answer. Unpause when you're done. And here we have the last 3 questions. Calculate the efficiency of an appliance which does 34 joules of work for every 200 joules of input energy. Give the answer as a percentage. Calculate the energy wasted by an appliance per second if its input power is 1500 watts and the useful output is 400 watts. And 8. Calculate the efficiency of the appliance and write it as a decimal. An electrical device wastes 0.7 watts when it's supplied with 5 watts. Calculate its efficiency and write this down as a percentage. So you just have to use that equation, useful energy out, energy input. I'm sure you can do them. I believe in you. That is the last one. Love you. Bye.